Yeah, yeah. These telecoms, yeah. Right. Next problem. Which is a capacitor of 150 microfarads. In series with 6 ohms to a step input 50 volts. Use Laplace transforms to determine an expression for the voltage across the capacitor during the transient period. So again, if we was to graph this, what would we expect over time? You'd think that, yeah? Well, we assume, unless we're told as a step from 10 to 50, we assume 0 to 50. So you're expecting the capacitor to start here. That's a sensible idea. We're assuming that's discharged if we haven't been told so. Yeah, and that it's going to gradually rise over time. So it's more likely that we're this time with that estimate. Okay. So, first thing we need to do, Ben, is let's go through step by step. So the first thing we do is, so we write an expression for ZS, which is 6 for the resistor plus 1 over 3 zeros 1 5 S. Yeah. So that's an expression for our impedance, and then we want an expression for the voltage. Where do we go from here? Voltage divided. So we can write an expression for VC in the S domain from the voltage divider rule, which is the input voltage in the S domain times ZC in the S domain over I'll remind myself of it, ZS. Because we haven't got an expression for the current. We can't use that Ohm's law way of doing it, but we can use the voltage divider. So, writing that out, VS 50 over S times ZC S is 1 over 0.3015S. Divide that by I've got 5 in the answers and that's 6 on the drawing. We better change it to 6 on the draw, 5 on the drawing, then, don't we? Well, that's easier than me changing all the numbers, Dom. Isn't it? Right. Underneath 5 plus. I've got to change that to 5. 1 over 0.0015 S. Yep. All happy with that. Now we got over here we've got a fraction divided by a fraction. So we can write 50 over S times all over wait a minute. No, hang on, you can't do it like that, it's wrong. This bit here is effectively over 1. So that's got to become 1 over to turn up. So you've got to have that on, you've got to multiply, so that's all of that times 1 over 0.0015S times 1 over 5 plus 1 over. Can I? Agree? Do you want to agree with that or not? So on the top, we've got keep that 50 over S there and multiply. On the top we got 1. Yeah. And on the bottom we've got, and that might help put these in brackets to see this, times 5 plus 1 over. That looks more like a 5. So when we multiply these brackets out, what do we get? Keep the 50 over s there, times 1 over. So we've got to do 5 times 0.015. Yeah. And then we multiply that by that. Cancels out to 1. Now we've got to do this multiplication. So 50 times 1 is 50. And then we're going to keep them separate. We're going to multiply everything there by s. To end up with that. Okay, closing the brackets. Yeah. So now we have to write those. So using partial fractions. But really, there's no substitute for practicing these questions so that you know when you see a particular thing what you've got to do. So using partial fractions, we can say that 50 over s times is equivalent to I over s plus b over s plus 1. Or follow that so far. What we got to do next in solving partial fractions? That was when we multiplied out the 5. When we multiplied that 0.3015s there by that 5 in there. Well, when you multiply 1 over 0.00515x by, that cancels to 1. All right, Ben? Yep. So what's the next thing in partial fractions then? What do you need to do to this side so we can solve it? Yeah. Put RH right hand side the common denominator. So we have to write that as equivalent to 50 over s times 0.3015s is equivalent to plus 1 is equivalent to, okay, so what we want is to be able to write the one common denominator, s times 0.00015s plus 1 underneath there. To do that, we need to multiply a by all right, this is should all be 0.75 now, shouldn't they? I'm back. Seven five. That's just 7.5. That's 7.5. And that's 7.5. Alright. Well spotted. Okay. And then that's going to be plus hang on, that's plus B on, not on the end there, isn't it? Close that, plus BS there. There's a load of BS. What's the next thing in the process of solving partial fractions? Yeah, so, but what are you doing then? Just so as everybody understand the process, what's the term for what you're doing there? Called equate the numerator. What you're saying is, because the denominators are exactly the same, yeah, you can say that 50 is equal to, so you can say this numerator is equal to that numerator. So you can kind of throw the denominators away for a minute and just concentrate on the numerators. Yeah. So you can say now that 50 is equal to I times 0.3075s plus 1 plus BS. Then you start to say, what can I do to make one of those terms equal to 0? So you rightly said, let S equal 0. Therefore, 50 is equal to I times 0 plus 1, and that's 0, so that bit's 0. I equals 50. Yep. Agreed? Then we've got to do something to make this side equal to 0. We let I well, actually, yes, that equal to 0, because if that equals to 0, then the whole term will equal 0, won't it? Yeah. So this we can say 0.0075s is equal to minus 1. S is equal to minus 1 over 0.3075 which is minus 1333.3. So we can now say, therefore, 50 is equal to minus 1333.3 times B. B is equal to 50 over minus. Which is minus 0.035. 375. Just check those. Just check those calculations with your calculator, please. Just in case the only error with that 6 and 5 was right. But check those answers that you get those values. For S and B. Alright, so now we can go back to our partial fraction there and put in the constants A and B. So we can write now that VC in the S domain is equal to I, which is 50 over S. That's minus 0.0375, which is B, divided by 0.0075 S. Now, this one looks like something in the table. We can deal with that. What we got to do to that side? What do we need to do? What have we been doing with something that looks like that? Just on that bit. Get S on its own. Divide by 0.3075. If we do that, we get S on its own. We end up with VC in the S domain is equal to 50 over S minus 50 over S plus 0.02. Yep. So that bit looks like a constant, but if we look at our table of Laplace transforms, A over S transforms back to step. So we can now transform back this bit goes to, we're looking at VC at time t, this bit goes to 50 and a constant over S plus another constant is I 50 E to the minus 0.02 t, which can be more succinctly written as 50 times 1 minus e to the minus 0.02 t volts. So where you end up with partial fractions in these problems, you're going to end up with a two-part solution like this. We'll see in a little while, then numbers don't always end up the same. You can't always factorise that constant in there. Okay? That's the graph you get from that function, exponential rise to a limit. So the capacitor gradually rises up to a limit of 50, which is what you would expect, and that's what we found in the science in year 1. Okay. And going back to here, we need to correct this mistake. That is 11333, you know. Okay, so I've corrected that now. Sorry about that. I need to make sure I go in the notes and correct it as well. Right, we're doing question question 5. Right, we've got an inductor, has a resistance. So there's an inductor, and it's got its own resistance, so we can mimic that as being a series resistor. A resistance of 4.5 ohms, an inductance of 22 millihenries, connected to step voltage of 45 volts. Yep. Determine the expression for the current during the transient periods. What do we think it's going to be over time? Sorry? You think exponential rise to a limit again, yeah? What's the limit? $45? Which is? So we think the limit's going to be 10. If you can do this, that might help you. Have I got the right answer? How is it what I would expect? So if you can understand the circuit and be able to sketch something, not in all cases, the RLC circuit is trickier because you don't know what kind of response you're going to get. But if you can do that, that can help you know whether you got the right looking answer or not. So, if we're expecting that, what kind of maths are we expecting to do here? Exponential rise to a limit. Well, we've just had exponential rise to a limit. What did we have to do? More importantly than that, we had to manipulate partial fraction. Yeah. So yeah, because we're predicting that, we're predicting this to be something along the lines of IT is equal to a constant I times 1 minus E to the minus BT. We're predicting it to look like that. And therefore, if we're predicting it to look like what we did in the previous answer, we're probably going to be doing the same maths for fractions. So because that is going to give us that kind of response, isn't it? Yeah. You're going to end up with partial fractions. So ZS here is Jasmine. .5 plus what do we do? Look at your Laplace transform table and see what you have to do for an inductor. It's minus 3 millihenries. Yeah, so you're right. But I would recommend you write it like that. Yeah. Just in these problems, that's probably easier not to use the power of 10 notation and get a bit messy. All right? But just be careful that you get the right number of zeros. And Vs is 45 over S for a step input. Therefore, Is is equal to 45 over S divided by the impedance, which is 4.5 plus 0.022 S. Yeah. And then what do we do to that? Fraction divided by another fraction. We'll flip it over, so we say 45 over S times 1 over 4.5 plus 0.022 S. And then we can say that's 45 on the top, and that's S times 4.5 on the bottom. Right, Ben? After that, Jake? Yeah. So next, how can we write that now? We could say that's we can go that 45 over S times 4.5 plus 0.0002 S is equivalent to, and write it in partial fraction form, I over S plus B over 4.5 yep, partial fraction form, and then we want a common, because we want a common denominator so that we can equate the numerators. We write the bottom line like that, and we write the top line as I times 4.5 plus B times S. Yeah. So perhaps a little note in here. Write as partial fraction in there. So you know what you're doing. And then we equate numerators. So we go 45 is equal to A times 4.5 plus 0.202 S plus BS. Yep. Let S equal 0. Therefore, 45 is equal to I times 4.5. I equals 45 over 4.5 equals 10. There. Done that. Then we need to let 4.5 plus 0.02s equals 0. Yeah. So 0.002s equals minus 4.5. Sorry? I've got minus 0.22 I've got. Have I written them numbers down right there? Oh, hang on. What? I'm right. B should come out with yeah. Yeah, I can see. Was it 204? Put the 4-5 in there. So therefore 45 is equal to B times minus 204.5. B equals 45 minus 0.22. Yeah, now we're on the right track. Okay. So then we can put those back into the partial fractions we had earlier. So we can say IS is equal to A, which is 10, over S minus 0.22 over 4.5 plus 0.022 S. Now what do we need to do? Yeah, so we want to divide by so we can write 10 over S minus, and that comes out at 10 now, I hope. And 204.5 plus S. Now we can transfer back. Because that looks like A over S, and that looks like A over B plus S. Yeah. So we can say I at T is equal to 10 minus 10 E to the minus 204.5 T equals 10, 1 minus E. That is what we expected, an exponential rise to a limit, the limit being 10. Yeah, 10 amps. And if we look back at the circuit, during the transient period, the inductor is going to induce some voltage that is going to oppose the current that's making it happen, and therefore it's going to hold the current flow back. But eventually, when everything settles down, you're going to have a current of 45 volts over 4.5 ohms is 10 amps. Yeah. So understanding that underlying principle can help you sketch what you think a graph might look like in some cases. Yeah. All right. So we'll put